Hello everyone, the title of my presentation is Identifying Bug Patterns in Quantum Programs. In this posting, I will first introduce quantum computing and quantum programming. Next is the bug patterns as well as our research motivation. Then an example illustrating the Qiskit program will be presented later, with a passing reference to the properties of qubits. After we have presented the specific bug patterns we have summarized, there is the final summary and the future work. Recently, quantum computing has the potential to solve extremely complex computational problems in chemistry, finance, machine learning, and so on. With the advent and progress of quantum computers, many quantum programming languages have been designed to implement quantum algorithms. Quantum programming is the process of designing and building executable quantum computer programs to achieve a particular computing result, and is drawing increasing attention recently. A number of qubit programming approaches are available to write quantum programs. In recent times, the current research so far in quantum programming is focused on problem analysis, language design, and implementation. Even though program debugging and software testing are important, they have received a little attention in the quantum programming paradigm. Until now, only a few approaches have been proposed for testing and debugging quantum software, and none of the previous work has focused on the bug pattern identification in a quantum programming language. The testing and debugging issues remain a big problem for quantum programs. Bug patterns are erroneous code idioms or bad coding practices that have been proved to fail time and time again. They are usually raised from the misunderstanding of language features and the misuse of positive design patterns, or simple mistakes having common behaviors. The information on bug patterns provides a basic for further research on debugging quantum programs. It provides insight into the possible consequences of different bug types and summarizes the common behaviors among similar ones. Also, it can be used to recognize faults that have been already existed and prevent potential bugs. In summary, the bug patterns taxonomy for quantum programming languages could be seen as a starting point for creating the general bug patterns for quantum programming languages. For identifying and classifying some bug patterns in a quantum programming language, and briefly discusses how to eliminate or prevent those bug patterns, we have chosen the widely used quantum programming language tool, Qiskit, as our target language and have identified common bug patterns. Qiskit is a Python-based quantum programming language that allows us to create algorithms for quantum computers. It provides tools for creating and manipulating quantum programs and running on prototype quantum devices and simulators. By focus on the language features of Qiskit and the execution sequence indicated by the circuit diagram, we can classify a quantum program into the following four categories. The initial stage is to initialize the quantum registers to store the qubits that need to be manipulated. Then the classical registers are initialized to store the values of the measured qubit. This stage does not include citing the quantum state, as the quantum state citings need to be implemented by a gate operation. Gate operation is the core of quantum computing, which is to operate on qubits. In quantum language, complex gate operations are decomposed into basic gates and gradually released. And if we want to obtain the output, we must perform a measurement operation on the target qubit. The measured qubit is returned as the classical state's value, which no longer has superposition properties. Delocation is crucial to receive and release the qubits safely. Otherwise, the auxiliary qubits in the entangled state will affect the output. This is a simple Qiskit program that illustrates the entire workflow of quantum program. In quantum computing, the basic unit of information is qubit. As shown in the figure, the first step means assigning a quantum register of 3 qubits, and the value of each qubit is 0 by default. Next, let the first and the third qubit pass through the Hadamard gate so that each qubit can take on values of 0 and 1. And in the next step, the first qubit is entangled with the second qubit through a control NOT gate to make the same value of the first and the second qubit. Finally, the output of this program will be the following 4 cases. According to the previous explanation of the execution process of quantum programs, we divide the bug patterns into the same 4 categories. For initialization, since the programmer does not intend to measure some qubits, it is assumed that there is no need to initialize the classical bits equal to the qubits. Nevertheless, this is also the reason why most programs go wrong. For gate operation in Qiskit, control gates are parameterized by 2 qubits, and the double controlled gates require 3 qubits. But this doesn't mean that the double control gates operate on 3 qubits at the same time, so many errors may occur. For the necessary measuring operations, the qubit that has been measured cannot be used as a control qubit to entangle with other qubits. Finally, no handling all the qubits in the entangled state can cause problems or output unsatisfactory values. Now let's see some samples of bug patterns in Qiskit. The first pattern is unequal classical bits and qubits. In Qiskit, each classical bit in the classical register stores a measured qubit value. Therefore, it is better to initialize quantum registers of the same size as classical registers. That is because from the point of view of program integrity, every used qubit should be measured. As shown in the figure, when we want to measure the third qubit, we received an error message, and if we do not measure one of the qubits, then a qubit will not get reset in some backend. Another case is that the number of classical bits in the classical register is longer than the qubit, unless we encounter the need to use multiple classical bits to store a qubit measurement. Otherwise, we do not recommend this operation. Second is custom gates not recognized. When defining a custom gate in a program, some programmers will want to define a basic gate that controls more than 2 qubits directly. This is certainly not an option. As shown in the figure, this pattern refers to a custom gate that does not use the gate class provided by Qiskit correctly. In other words, Qiskit does not recognize the custom gate. This bug pattern is mainly caused by programmers do not really understand quantum gates, so the correct custom gate should be a composite gate combining the basic gates provided by Qiskit and applied to the circuit. The third pattern is easy. It's parameter misuse of complex gate instructions. In quantum experience API error codes, there is an error indicating that the instruction is not in the gate of the core. This error is because the complex gates in Qiskit do not support label or control state as parameters as that for basic gates. So if the programmer lacks some knowledge about double control gates or other complex gates and use the parameters from these gates as that for the basic gates, it probably leads to this kind of pattern. The next pattern is insufficient initial qubits. This figure shows a part of the code for the VQE algorithm. When defining the VQE solver method toLocal is used, then a toLocal parametric circuit consisting of alternating, rotating, and entangled layers can be formed. As the toLocal circuit is parameterized, circuits consisting of alternating rotation layers and entanglement layers. If the number of qubits of the variational form does not match, the desired result is not obtained. So it is important to initialize the values supported by the parameter num qubits when using parametric circuits or methods involving quantum entanglement. The next pattern is multiple or repeated measurement. Some simulator backends are unable to execute the circuit when the measurement operation performed on the qubit is repeated too many times. Alternatively, some methods such as see-if are called but do not give the correct result. This is a test used to measure the quantum characteristics in a computing backend simulator repeatedly. The programmer used the Qiskit Air Simulator backend and the Python-based quantum simulator module Basic Air to simulate the circuit. When we call Basic Air, the system may report an error. And when we call the see-if method, the qubit of the MIG register did not achieve flipping. In summary, we do not recommend excessive measurement operations on qubits because it can make the system extremely unstable. This example is quantum teleportation protocol, and the pattern is incorrect operations after measurement. In the code, the last qubit state should be changed according to the first qubit's measurement results. Entangle the measured qubits with the unmeasured qubits is no point, because the result of the measurement can be treated as a classical value that no longer has the property that the qubit has. If the measured value continues to be entangled with other qubits, which is used to change the target qubit state, it will affect the real output. This mistake is quite common. Many programmers inadvertently used measured qubits. And the last pattern is unsafely on computation. Qiskit is a compelling framework because it supports the automatic management of qubits, so there is no need to do the work of unallocated qubits manually. However, as different program languages such as Q# have their own implementations, which can lead to exceptions in different backends and the need to manually unallocated qubits. Considering the commonality of bug patterns, we need to include this pattern in the scope of our present study. Now we have identified some bug patterns in Qiskit to provide both researchers and programmers a clear view of what kind of bugs may happen in quantum programs. Quantum programming introduces new quantum-aware bug patterns that differ from existing classical bug patterns. These quantum bug patterns should be identified, and a catalog for these patterns should be presented. In the table, we list the bug patterns in Qiskit we identified, and more bug patterns will be added to the list as we get some new progress. In our future work, we will cover other remaining quantum-related constructs as well as the interactions between them. We'd like to investigate more bug patterns in real programs of Qiskit and other quantum programming languages. After that, we would also like to develop a bug detecting tool based on the identified bug patterns to support bug finding in Qiskit programs. We hope this report can be helpful in writing bug-free quantum programs. That's all. Thanks for listening.